We're going to talk about section 712, periodic trends. We're going to cover several different concepts. First concept is effective nuclear charge, Z effective. This is the charge that the outer electrons feel. The charge felt by outer electrons. The core electrons are shielding these outer electrons. So the charge felt by the outer electrons is not the total nuclear charge Z. We're talking about the effective nuclear charge. It's really important that you recognize the core electrons are shielding some of the charge of the nucleus. So your effective charge felt by the outer electrons, it's approximately equal to the number of outer electrons. It's an oversimplification, but it works for what we're going to be talking about. It's a simplification that is good enough for us for now. So as you go left to right in the periodic table, you add more protons, and you're in the same shell number, left to right. So the number of outer electrons are increasing, the number of protons are increasing, Z effective is increasing because those, even though we're adding electrons, they are not shielding the outer electrons from the charge of the nucleus in the same way that the core electrons would. When we go up and down in the periodic table, Z effective is approximately constant. Now this might be counterintuitive because when you go up or down in the periodic table, when you go down, the number of protons is increasing, but the number of outer electrons is not. If you're in the first column of the periodic table, your number of outer electrons is 1, no matter what you are. Anywhere in that first column, you have only one outer electron, and it's your number of protons minus 1 is how many core electrons you have, and those core electrons are shielding that outer electron from much of the charge of the nucleus. That's if you're in column 1. If you're in column 2, you have 2 outer electrons. So your core electrons would be your total number of protons minus 2, because there's remember protons and electrons are equal. So if you have 2 outer electrons, and electrons or protons are equal, then all but 2 of the protons are being shielded, mostly shielded. It's not that simple, but again, it works for what we need to know for this class. It's beyond the scope of this course to go into a full discussion of effective nuclear charge. Okay, next thing we're going to talk about is ionization energy. And this is the energy required to remove an electron from a gaseous atom or ion. And here is our reaction equation for the first ionization energy. We're taking off 1 electron from a gaseous atom. The second ionization energy would be taking off 1 electron from an atom with a +1 charge, because we've already taken off 1 electron, which would be our first ionization energy. So now we're on our second. So what do you think the third ionization energy would be? Hopefully you figured out. We'd start with the +2, an ion with a +2 charge, because we've already taken off 2 electrons. We take off a third electron, and we end up with a +3 charge. And we can go on, the 4th, the 5th, the 6th, the 7th ionization energy. So let's look at some trends. This I1 through I7 is just representing the first ionization energy up through the 7th ionization energy. And now we are looking at, let's see, the third row of the periodic table, sodium up to argon. And if we look at the first ionization energy, the atom losing its outer electron, you see that there's an increase in ionization energy as we go from left to right in the periodic table. Ionization energy increases as we go left to right. Right now it looks like we're going up and down, but sodium is on the left, argon is on the right in the third period. Remember, a period is a row in the periodic table. So let's think about why is that? So ionization energy is the energy needed to remove an electron from an atom. We're talking about just the first ionization energy here. So if we're going to remove an electron from sodium, sodium has 11 protons. Sodium's number 11. 11. It's hard to see that. And let's see, argon is number 18. Number 18 over here. Sodium 11, argon 18. So sodium's got 11 protons, argon's got 18 protons. Who's holding that electron tighter? Sodium with 11 protons or argon with 18 protons? Hopefully you realize when you go left to right, the number of core electrons remains the same because we're just adding outer electrons here. So our effective charge is going up. And since our effective charge is going up, we're holding on to the electrons more strongly. Since we're holding the electrons more strongly, argon has a bigger first ionization energy than sodium. So sodium's got a weak grip. It only takes 495, this doesn't tell you what these are, I'm assuming they're joules of energy, to remove an electron. This must be for 1 mole of atoms. I'll have to look in the book for the actual units here. Okay, but really important, when we go left to right in the periodic table, ionization energy goes from a small number to a large number. Okay, so when we go from the top to the bottom of the periodic table, the atoms get larger because we have more shells of electrons. N is increasing when we go from the top to the bottom. The outer electron is farther from the nucleus, so it's easier to remove. So the ionization energy goes down. Ionization energy is how much energy you need to pull that electron. If the electron's easier to remove, ionization energy goes down. So here's a summary for Z effective and ionization energy. So when we go up bottom to top of the periodic table, Z effective is approximately constant because the number of protons does go up, but the number of outer electrons is constant in a single column. The number of core electrons is increasing, so even though we have that increase in protons, we don't have a large increase in Z effective. The ionization energy goes up as we go up the periodic table because N, the number of shells, decreases. So we're getting smaller and smaller atoms. The outer electron is closer to the nucleus, so it's harder to remove it. It takes more energy. Now, going left to right, Z effective is increasing because we're getting more protons in the same shell. The electrons are being added in the same shell, so there aren't any more core electrons. The ionization energy is going up because there are more protons holding the outer electrons in place. So it's harder to remove those outer electrons. There's a bigger force holding them. So the energy required to remove an electron is increasing. Okay, the next periodic trend we're going to look at is the atomic radius. And the atomic radius is the distance from the nucleus to the outer electrons. And we have several different ways in which this changes. It's not random, it's very ordered. When we go left to right, atomic radius decreases because the effective nuclear charge increases, so electrons are pulled in more tightly. You have more protons as you go left to right. And as you add more protons, you're not adding any core electrons. So those core electrons, there's no extra electrons shielding the outer electrons. You have more protons, the effective nuclear charge is going up, and it pulls in those electrons, those outer electrons, more tightly. When we go from the bottom to the top of the periodic table, the atomic radius decreases because the number of shells is decreasing. So as shells decrease, the size of the atoms are getting smaller. And on the left side, you're going to see a summary. These are the actual sizes in angstroms, I believe, of the different elements. Not all of them. It's got the first 2 columns and the last 6 columns. So we see hydrogen and helium are super small, and we go from helium all the way down to radon. We get bigger, 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 bigger. And when we go from left to right, we're getting smaller, 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 except you'll notice bismuth has a little bit of an exception there. Do we see any other major exceptions? These 2 look like they might be smaller than tellurium. We're not going to worry about those exceptions. So we're just going to worry about the general trend. So when we go bottom to top, AR, atomic radius, goes down because N, the number of shells, goes down. Left to right, atomic radius goes down because the effective, or the number of protons, goes up. All right, there you have it. All right, the very last thing we're going to go over is comparing the first, second, third, fourth, fifth, sixth, seventh. When do we get these huge increases in the ionization energy? If we look here, notice, for sodium, first ionization energy, second ionization energy. See this tenfold? There's a tenfold difference here. Sodium has one outer electron, so here we're taking off the one outer electron. And then the second ionization for sodium, we're taking off an inner core. This is for an inner core electron. Huge amount of energy taken to remove an inner core electron. Let's look at magnesium. Magnesium has two outer electrons. So the first two ionization energies, it doubles. First two, for those two outer electrons. But all of a sudden, the third ionization energy for magnesium, huge compared to the second. So all of a sudden, there's about a five-fold increase because here we are taking off the inner core electron for the third ionization of magnesium. Now, how many outer electrons does aluminum have? Hopefully you can see aluminum has 3 outer electrons. So we remove the first, the second, the third electron, and ionization energy is increasing when we go from first to second to third. But notice, all of a sudden, there's this four-fold increase when we go from the third to the fourth ionization energy. Because for the fourth ionization energy for aluminum, we're removing a core electron. So that first core electron that you remove, it takes a lot of energy. So if you see data on ionization energy, first, second, third, fourth, fifth ionization energies, you can figure out how many outer electrons an element has because the huge jump is the first core electrons. So it's 1 minus the huge jump tells you how many total outer electrons you have. So here's our huge jump. So we have 1, 2, 3, 4, 5 outer electrons for phosphorus. And indeed, if you check, phosphorus does indeed have 5 outer electrons. That's it for this section.